The next topic, that is the moving coil galvanometer. Galvanometer is the device with the help of which one can detect or measure very small amount of current. This one is the galvanometer which we use in laboratory. Okay. Now this one is the schematic diagram for its construction. Okay. So in moving coil galvanometer, we can say the principle on which it works, that is the torque acting on the current carrying coil when it is placed in the uniform magnetic field. On that principle this works. Clear? We already studied in the theory. When any current carrying coil is placed in the magnetic field, the torque acts on it, and due to that it will be rotated. Now see here, in the construction of this one, two cylindrical type magnetic poles north south are there. So due to this type of shape of the magnetic poles, the magnetic field that will be a radial one. Okay. Now in this particular magnetic field, a coil is placed. See, this one is the rectangular coil placed in the magnetic field. So here the plane of the coil is in the plane of the uniform magnetic field. So we can say the area vector for the coil that will be perpendicular to the magnetic field. Then here, for this particular coil, one axis is attached with this one, and then it is pivoted from upper and lower side. So with respect to these two support, it can rotate like this. Okay. Now, when the current is passed through this one, the torque will act on it. So this will be rotated in this way. But now here, with this axis of it, a spiral spring is attached. So when this one is rotated like this, the torsion will be produced in the spring. So spring will produce the restoring torque. So when the torque acting on the coil and the restoring torque produced in the spring both becomes equal, then your coil will be steady. Now one pointer is attached with the coil. So as coil rotates, that pointer will be also rotated. It will show you the deflection. So when the coil becomes steady, this pointer will be steady on the scale. Now, initially, by giving known currents to this galvanometer, the scale is already calibrated. So with the help of this steady pointer, you can measure that particular very small current, or due to deflection of this one, you can say yes, the current is there in the circuit, so we can detect the presence of current. Clear to all of you? Now torque acting on the current carrying coil placed in the uniform magnetic field, that is given by the equation NIAB sine theta. But here the area vector and the magnetic field are perpendicular to each other. So theta, that is 90. So sine theta, that is sine 90, that is equal to 1. Now in this particular case, the torque acting on the coil, that becomes maximum one. So we can say here tau maximum acting on the coil, that is NIAB. Now When torque acting on the coil and restoring torque due to spring becomes equal, then coil will be steady. So we can write the restoring torque, that is K into phi, that is NIAB, where K, that is known as torsional constant. Torsional constant of the spring means restoring torque produced per unit deflection. Phi, that is the deflection. So per unit deflection, whatever the restoring torque is generated, that is called its torsional constant. So from this equation, we can write phi, that is equal to NAB upon K into I. Torsional constant, that is the constant for the given spring. N, that is number of turns, constant one for the given coil. Area of the coil constant. B, that is uniform one, so constant. So here we can say phi, the deflection, that proportional to current I. So if more current is passed through the coil, more deflection will be obtained on the scale. If less current is passed, then less deflection will be there. Clear to all of you? Now, deflection per unit current passed through the coil, that is called its current sensitivity. So we can write the equation for the current sensitivity of the galvanometer. So that is I S equal to phi upon I. That is nothing but the deflection per unit current passed through the coil. And we can write that is NAB upon K. So from this one, you can write the equation for voltage sensitivity also. Say, here on both the side, multiply by 1 upon R. So phi upon IR, IR, that is voltage. So phi by V. So that is nothing but the deflection per unit potential difference. So that is NAB upon KR, and that is called voltage sensitivity of galvanometer. Clear to all of you?